Hi everybody, this is Rabbi David Fohrman, and welcome to Parshat Va'era. You are watching Aleph Beta. Last week we spoke about a midrashic analysis of one of God's names. This week I want to talk about a midrashic analysis of another of God's names. In this week's Parsha we meet the name Shakai. Shin Daled Yud. We pronounce it Shakai in deference to not using God's name unnecessarily. And the sages had an interesting interpretation of this name. They saw it as an acronym for the words Mi She'omer Lo Dai, he who said to his world, enough. So what does this mean to say to your world enough? So I cannot profess to know exactly what this means, or even exactly what it is that the sages meant when they said this. But I will tell you the thoughts that their language inspires, at least in my mind, when I hear the God who said to his world enough. You know, the sages lived long before theories of modern cosmology. But that declaration, he who said to his world enough, really seems, in my mind, to evoke thoughts of things that scientists, astrophysicists say in our day and age about the very early universe. As it turns out, the universe really did need reining in. Had God not said to the universe, enough, you and I probably wouldn't be here today. Let me review with you some of where modern cosmology is at in understanding the very beginnings of what we call creation. There was a cataclysmic explosion. Somethingness came from nothingness. The Big Bang. According to modern physics, time itself, as well as space, came into existence. You can't say what happened before the Bang. There was no before. In this massive explosion, everything begins. And what was there after the explosion? At first, all there was were these subatomic particles racing out from the center. There weren't even any atoms yet. Over time, the super hot subatomic particles speeding out from that initial explosion cool to a level that visible light first becomes apparent. And in a blaze of brilliance, light comes into the world by Yeor. Over time, the force of gravity begins to cause these subatomic particles to coalesce, to draw near to each other, until the first, simplest atoms are formed. Hydrogen atoms. Hydrogen is the most plentiful element in the universe. It's a single electron orbiting around a single proton. And for a long time, that's all there is in the universe. These huge clouds of hydrogen. But slowly, gravity draws the clouds closer together, and friction between the hydrogen atoms causes the hydrogen to heat up, until the cloud becomes so dense and so hot that it ignites in a thermonuclear reaction. The hydrogen burns and transforms itself into helium. We call these burning clouds of hydrogen stars. Now, for a long time, there was a universe with just stars in it. How did we get the rest of the universe? So it turns out that if a star is big enough, if it has enough mass, towards the end of its life, as it nearly exhausts all of its hydrogen fuel, gravity begins to cause the star to implode upon itself. And now, as the star caves in on itself, the star explodes in a mammoth explosion that we call a supernova. In the white-hot kiln of a supernova, all of the heavy elements are formed. Carbon, gold, zinc, copper. These elements are cast out into space and become the building block of things that we call planets. Before you know it, you've got a universe going. So it all sounds fairly simple, right? I mean, you start off with a Big Bang, and pretty soon you've got stars, you've got planets. Not so tough, right? But here's the interesting thing. The Big Bang, as you'll recall, was an explosion. Now, typically, explosions are not terribly ordered things. If I threw a grenade into a room and you surveyed the scene afterwards, it's going to look pretty chaotic. There'd be splotches of debris over there, shattered glass over here. It's the ultimate random event, an explosion. The problem is, the Big Bang couldn't afford to be random. We wouldn't have the universe unless it was very, very finely tuned. Let me explain to you what I'm talking about here. There is something that cosmologists call the Flatness Problem. It goes like this. Remember, right after the Big Bang, you have all these subatomic particles speeding out into space. How fast were they going? You see, if they were going a little bit too fast, gravity never would have been able to act upon them to bring them together into atoms, to bring those atoms together into clouds. And all you would have had is a universe of subatomic particles, no stars, no planets, no nothing. Okay, so they can't have been going too fast, but what if they'd been going a little bit too slow? Then gravity would have stopped the acceleration altogether and brought everything back into one big crunch, and you wouldn't have had anything. Okay, so it had to be just right, not too fast, not too slow. But now you might ask, well, what was the margin for error here? I mean, I guess we were pretty lucky living in this just right universe, but how just right did it have to be? What if I told you if the rate of expansion were 10% faster than what it was, we wouldn't have a universe. And if it were 10% slower than it was, we wouldn't have had a universe. So you'd say, oh, we're pretty lucky, we had 9 chances out of 10 of not having a universe, and we got lucky, and the 1 chance out of 10 prevailed, and here we are. Okay, but what if I told you that it wasn't 1 out of 10, it was 1 out of 100? 1 part in 100 faster, no universe. 1 part in 100 slower, no universe. So you'd say, well, I guess we're really lucky. So what is it in fact, then? Is it 10%? 1%? 0.1%? So cosmologists have estimated the actual margin of error here to be 1 part in 10 to the 54th power. That's your odds here. 1 part in 10 followed by 54 zeros. We don't make names for numbers that big. To give you a sense of this, it is estimated that all the leaves on all the trees in all North American forests, that's about 24 zeros, 10 to the 24th power. 10 times the amount of leaves in all the forests of North America, that would be 10 to the 25th power. We now think that all the atoms in the observable universe, that's about 10 to the 81st power. So somewhere between that, somewhere between all the leaves and all the trees in North America and all the atoms in the universe, 1 part in that haystack, that's the chance you have of having a universe with stars. And remember, there's only one bang that we know of. I mean, this is our universe. Either it works or it doesn't. But it's not just the flatness problem. There's other problems too, like the smoothness problem.
Thanks for watching. You can enjoy the rest of this video by going to aleph-beta.org. Just click the link below.